irresistible force meets an immovable object. If you do not actually understand the question, and now we're going a little bit of what can happen at uni, is you take this, this phrase apart word by word and go for the words that you don't understand. So you ask yourself, what's an irresistible force? Or can you find words with that describe it? Yeah, so if you never come across that sentence or that phrase, what we state, what is an irresistible force? And I ask friends and students around what comes to mind when you have an irresistible force. And they call it like a tsunami, a big wave, or a volcano eruption, then an avalanche. So pretty much everything big and that we don't control from nature. And maybe some fiction. But what is an immovable object? I asked the same questions to friends. And they came up, well, the front row of the Crusaders. A movable object. Compared to what? Or a mine truck, mining vehicle. It's pretty massive. Some of your parents probably would say, mortgage is an immovable object. You will hit that soon, maybe. But what is now the question? What happens when an irresistible force or an unstoppable force, which is another word, meets an immovable object? So the first thought that would probably come to mind is when an irresistible force hits any object, for that matter, you would think it moves, right? You have like a large avalanche wave coming. It would make things move. But here we go, we say it's an immovable object. So here's the paradox, that any object whose momentum or motion cannot be moved, or changed for that matter, is an immovable object. And for that matter, it holds also any object that is pressing against that immovable object, creating an unstoppable force. Does that make sense? So it's always in balance. The problem or the paradox here is that we deal with two extremes, an immovable object and an unstoppable force, which are the same. An unstoppable force can be also identified with an object or force that has an infinite inertia. And so the problem that we face in reality is now, have we experienced an immovable object? And the answer is no, unless you convince me that you've seen something like that. You have always objects that do move, and the whole thing is falling apart. You know that equation F equals ma. And on the right-hand side, you see that change of momentum. Momentum is mass times velocity, and so the change of mass times velocity is the change of momentum, which is balanced, dynamically balanced, by the force acting on that object. Don't worry, I don't want to go into further details, but I want to bridge it now to what the study of this motion is and how it relates to what you might be interested in studying and pursuing further. So the next slide is loading. While it's loading, we see in life that all things, whether small or large, cosmic or micro, are moving. You see in the upper left corner atoms in motion. You see bacteria that create a motion by itself. So bacteria flagellate motility. Here you see a very fast object in slow motion. So I'm encouraging you to go to these links. If you're interested in seeing me afterwards, to get you these links and to have don't need the tone. But you see things moving around. And we live in a relativistic space and time, so you always have to ask the question with respect to what? Change of momentum with respect to what? An external force with respect to what? And so the study of engineering that you might pursue is the study of looking at a particular reference frame that we live in and study what the performance of and force acting up on an object might bring, like in this slow motion shot. So, is that moving further? So that's where I wanted to go next. The question is relative motion, not an absolute. We don't have an absolute reference frame. We have a relative. And you always have to ask yourself the question, compare to what? So if you have that immovable object here of the front row of the Crusaders against a fly, which is supposedly the force, you can just add that fly momentum to the Crusaders line, and nothing would happen. So how would that change the equation F equals ma? Change of momentum. The Crusaders are standing still. External force, the fly. It's so negligible that you have no change of momentum, and that's called the conservation of momentum. So whatever the Crusaders were doing before would happen no matter whether the fly is touching or not. So that's the things that we study, for instance, engineering to perform or predict a performance. The other way around, here I have the force on the left-hand side, the object ma on the right-hand side. Surely even that big truck, a person, if you put a person next to it, would probably reach half the diameter. So that's the scale of that mining truck. Who would win in this? Left or right? Yeah, absolutely, but not necessarily because of the force, maybe, but certainly because of temperature and melting it away. So anyway, so the equation here is, again, is it force or momentum that changes? I would even say the lava that comes down the hill and with the heat is, in this case, the moving object, momentum, and in this case, the truck has nothing to do with what the lava stream is doing, the flow. So conservation of momentum, again, the lava would win in this case. So in terms of this question, what happens when an irresistible force meets an immovable object is we're dealing, they're equal to one another, but we're dealing with an extreme case that we have yet not seen in reality. So in terms of going forward, what you might be interested in learning and pursuing in life, you have an option if you're generally interested in science and engineering in that category. Albert Einstein said, scientists investigate that which is already in place. We just discover things. Versus engineers create that which has never been. And that is within perspective that engineers use what scientists have figured out to make it available for common life. Yeah, so in the upper corner, you observe something in nature, you discover its laws, and then you make it applicable. Either you exploit or you avoid something that you see and make it available through understanding and creating new technology that are helpful in life. And in the following, I want to go through some applications and career paths where you see things moving and what's behind the subject for the sake of your choice, what you might pick. So here we have, I always present you a picture or a subject, and then on the left-hand side or somewhere on the slide, I give you the key subjects that relate to that you study for that matter. So here you see wind flow as an example, tower, turbine, and you would study fluid dynamics, design, computation analysis. This guy here is the CEO and founder of WindFlow, UC graduate as well. And here are some students working on a particular project, which if you come to the open days in July, I can elaborate on that a little bit, because we have a unique program here at UC that no other university in this country has, which is called Final Year Projects, where we link up with industry partners and do real-life experience in the last year before you graduate. So that was one of the projects that we did. So we call this classical mechanical engineering. And the following slides, I'll let you guess what the next one would be. So here you see 4 objects that are not necessarily immediately related to mechanical engineering. But what do you see? What subject comes to mind when you see these pictures? Civil, yeah? You see a bridge, you see a house, multi-story house, you see a water power plant, you see a tower. Typically, absolutely right, civil. But even these objects cannot be done without mechanical engineers. Why? Because you have moving things in there. Whenever you see moving things, surely a mechanical engineer has been involved. So that's it. Mechanical interlinked with civil engineering. Next one, very hot topic. Bioengineering is so crucial. A tendency of need of engineers for biomedical stuff is on the rise. Here, all these pictures that I show you, we've been involved in one way or another. Here, a colleague of mine is doing research on the breathing mechanism, especially when you have, if you rely on gadgets and things like that to have the right application for your person. So small babies, elderly people, sports people, people with breathing problems, and people for surgery, for instance. And the study here is, what you see here is a CT scan of a real person. And since you can't make things visible easily, in fluid dynamics we talk, you increase the size and scale it up and send a fluid through. A fluid is one way of making the flow visible by coloring it or putting a laser to it, okay? So this is the increased system of the CT scan of a real person. We send some fluid through in an experiment, and now we can analyze pressures and velocities, and then design accordingly to come up with the device that a person needs. Mechanical engineering. Mechanical and biomedical engineering. Yeah? So if you're not sure where bioengineering sits, biomechanics, biomedical, and the technology behind, it's mechanical engineering. Here, a tetraplegic subject. If you have a limiting ability of using your arms, wheelchair people, you can study in which direction, this is the picture of the analysis, in which direction, in which angle you have the most power of your arms to be using for pushing a wheelchair. And so again, that would be in mechanical engineering, you study design, experimental analysis, manufacturing, management is in all cases there, and physiological modeling. And you do diagrams like that, and you figure out where, for that particular person, is the maximum strength. and you design the wheelchair accordingly. We see a prototype. Again, student project in their final year. What would it be? Mechanical and bioengineering once again. So we have to go a bit faster for the next few things. Here, an example of automated processes and robotics, electrical, electronic devices. You've heard about that one. Whenever mechanical and electrical / electronics comes together, you have mechatronics engineering. Okay? Here, an example of the water whirler from Len Lai. Len Lai is a fine artist person that had as a legacy, put a book together with all his kinetic sculptures that he wants to or wanted to build. And there's a Len Lai Foundation that UC is collaborating with and bringing these sculptures alive now. And we've done the water whirler in the waterfront in Wellington. So if you have a way of visiting, then go to the waterfront and have a look at that whirl. Again, started as a student project, and the driving unit that runs the water whirler was done at UC. Another one is the blade. If you have been here in last year, August to November, there was a Len Lai exhibition in the art gallery, and the blade was there as well. Again, the unit was done at UC. And here's the simulation to it, not needing to tell you that that was done in mechanical engineering as well. Mechanical and fine arts. And I skip or I go faster through the forensic engineering. Mechanical engineering, once again, has something to do with fluid dynamics again, retracking from a crime scene where the blood drops with what diameters have originated from, whether the person that murdered somebody kneeled, stood far away, what caliber of weapon was used, and so on and so forth. So that research is done here at Canterbury as well with one of my colleagues. So we have mechanical and law. So to wrap up, here's another one, forensic, with an explosion. I skipped that one. To come to my last slide, here's an example of robotics and mechanical and forestry, and the subjects go on and on and on. The list is endless. You can work as a mechanical engineer to forecast the weather, again, moving things, predicting the stock market, working for toys companies like Lego or Surprise Eggs, microbiology, manufacturing, sports, just to name a few, traffic control, traffic development, food processing, automation of products, harvesting, and acoustics as a last example. That's the Elb Harmonic Orchestra home in Germany, just recently opened last year, being in the category of the Sydney Opera House in the Guggenheimer Museum in Spain. So if you have a visit in Germany, try to get in. It's a fantastic hall. So essence of the whole thing, wherever you observe a motion, make the association that in some way or one way or another, it is associated with mechanical engineering. And what I can pass on to you, what to do now, what to do next, and how you should shape your future, is read. Be interested in something. Read what are open questions that you might be doing in a few years' time. Stay curious, main thing, and go through open doors. Never don't go through an open door that is opening up in front of you. Yeah? So just be encouraged. So that's me. Hope you see each other in the future.